which is chapter 5, radical functions. And as we study radical functions, this section of notes 5.1 is really important. It's the basis for a lot of the notation and calculations that you're going to see in chapter 5. So we're talking about rational exponents and radicals. And today we really want to be able to just understand how a rational exponent and a radical work together, because they're really the same things. And then we can rewrite from one form to another so that we can also evaluate things, and that will be helpful later on when we're solving. First, before we go to the next slide, I want to talk about the word rational, because we're talking about rational exponents. What math word is in rational? Math word. Ratio. Okay. So we're looking at this word ratio right here. And what is a ratio, or better yet, what does a ratio look like in math? Fraction. Perfect. Thank you, Kyle. So when I talk about rational exponents and radicals, I'm really meaning to say fraction exponents and radicals. Okay. So instead of having the polynomials like we had last chapter, where the exponents always had to be whole numbers, like 0, 1, 2, 3, 4, now we're going to mix in fractions. Okay, so we need to talk about something called radical or root notation. Okay, so go ahead and draw this picture. I'm going to name all the parts in the picture. You guys are really familiar with one version of this, which is the square root. But that notation can be used for a lot more than just the square root. So we call this radical notation because this symbol that I think a lot of you, if it were standing alone, you would call this a square root, right? That's actually called a radical. Okay, so I'm going to point to that piece right there. That's actually the radical. I hear everyone.
It's so scary.
Raise your hand if you think I'm staring at you all the time. Thank you. I just make really good eye contact. You should feel loved to know that I'm looking at all of you. Every day I see all 23 of you. Although I was really staring at you that time because I don't trust you now. You said something, no one will confirm it, and you said something. This piece right here is called the index, or we will call that the root. Now that number, like in text, will look a lot smaller than the other numbers. So it's kind of like almost looking like an exponent in size, but it sits in front of the radical. And then this number, the number underneath the radical, is called a radicand. This is a fraction. Oh, yes. Jacob, you're checking out. Please take your case. The notes will be online. So that's called the radicand. Sometimes I refer to it as the stuff underneath the radical, and then other times I say the word radicand. Okay, so they mean the same thing. The stuff underneath the radical is the radicand. Now, you guys, like I said, are very familiar with one version of this, right? If you saw that alone, you would say square root. The square root is actually this. a radical with a little 2 for the index, meaning square root. But square roots are so common, we don't have to write the index. Any other root, we have to put the little index number outside the radical so that you know it's no longer a square root. Okay, but if you see just a square root with no number, you know that truly there's a 2 right there. Okay, it's really a square root, so there's actually a 2. Okay, so then we're going to start to see things that look different. We could see something with an index of 3, and then I'll call that the cube root. Or I can see like a 4th root. And so you just read your index. 5th root, 6th root, 7th root. Square root and cube root are the only 2 that are kind of different. Does anybody have any questions about that notation stuff? That's going to be huge in chapter 5. Okay. Now, how does the radical root notation relate to this idea of a rational exponent, something that's a ratio or looks like a fraction? That's what we're going to investigate on the next slide. So I have 4 statements at the top of my slide. If you'll copy them into your notes, I've got a square root of x, I've got a cube root of x, I've got a 4th root of x, and an nth root of x. And we're going to take those radicals and write them as expressions that have fractions exponents. And I'll do the first 2, and then you guys will do the last 2, because you'll start to see a pattern. Anything that is a square root is actually taking the radicand, the thing underneath the radical, and raising it to a 1/2. So you're not squaring it, you're raising it to the 1/2. Anything that you're taking a cube root of, you're actually taking x to the 1/3. So not x cubed, but x to the 1/3 is the same as a cube root. So you guys tell me, what's the 4th root of x? X to 1/4, and what's any nth root? X to the n? 1/n, right? It needs to be as a fraction, and the root should be in the denominator, so we're going to write that down. The root, or you might call it the index from the last slide, is always in the denominator. So if I was taking the 8th root of something, that'd be like x to the 1/8. Can you all accept this? Okay. Now, we're going to go a little bit further, and we're going to look at how we can then manipulate some other expressions. Okay. And I'm going to take a page from yesterday where we were looking at properties of exponents, and I'm going to give you something that has a fraction exponent. So I'm going to take x to the 1/n, and I'm going to raise it to the m. Think about all your properties from yesterday. Maybe flip back in your notes if you want and kind of look them over. You've got a product of powers, a quotient of powers, power of a power, power of a product, power of a quotient, zero, negative exponent properties. Which one does this most resemble? Oh, you think power of a quotient because it has that fraction? Okay. What else does it look like? Let me ask you a different question. What should you do with your exponents? You can multiply them. So if you're thinking about adding your exponents, subtracting your exponents, or multiplying your exponents, most people would answer on this problem, because of the group of parentheses there, we should multiply our exponents. This one actually looks most like power of a power. I could see why you'd say quotient because it has the division right there, but this thing is not actually being divided, the whole x to the 1/9 or 1 over n. Okay. So to me, this looks a lot like a to the m raised to the n, and we were supposed to multiply our exponents. So let's multiply 1 over n times m. What do you get when you multiply 1 over n times m? M over n. Are you okay with this? Okay. Okay, so if I had something like x to the 1/3, and then I raise it to the 5th, I could really write that as x to the 5/3. Okay, using my properties of exponents. So the properties of exponents from yesterday apply to everything with a fraction exponent as well. So don't let the fractions throw you off, okay, and immediately think about quotients. They're actually just exponents. Now, big connection here. Then what's the nth root of x raised to the m equal to? The nth root of x raised to the m. Think about this nth root of x inside the group of parentheses. How else can we write the nth root of x? X raised to the 1 over n. And so then it looks like the line just before it. So the nth root of x raised to the m power is really equal to x to the m over n. Because we could substitute that piece on the left from the line above it. We could replace the nth root of x with x to the 1 over n. It really is just x to the m over n. Okay. So this piece right here in your notes, maybe box, circle, highlight. And this is very important. This is how you're going to rewrite. Okay. So like if something looks like a radical and you want to write it in rational exponent form, use this property that we have. If something looks like rational exponent and you want to rewrite it as a radical, then use this property. Okay. Note that our property goes along with the same statement that we made above in red. The root is always in the denominator. So if we're taking the nth root, then we're going to have n in the denominator of our fraction exponent. The other exponent that might be hanging out, like m, if I'm raising it to something, that's going to be up in the numerator. So that's what we're going to use to rewrite from rational exponent to radical form, vice versa, either way we want to go. So that's our next slide. We're going to look at some examples where all we do is rewrite. Okay, all we're going to do is rewrite it. Okay, so I'm going to start with radicals. If I have the cube root of 15, the square root of 11 raised to the 5th, and that's the 7th root of negative 42 raised to the 2nd, or squared. I want you to rewrite these so they have fraction exponents. Think about when you're writing with fraction exponents, the roots that you see are going to be where? The root is always in the denominator. Okay, so we're going to start with the cube root of 15. What's the root? 3. Where does it belong? In the denominator. So we're going to write 15 to the 1/3 and be done. Square root of 11 to the 5th. What's the root? 2. Even though you don't see it, there's really a 2 there because it's a square root. Where does the 2 belong? In the denominator. So we're going to write 11 to the 5/2. Will my fraction for the last one be 7 over 2 or 2 over 7? 2 over 7, why? Where is the root? Somebody besides Kylie. Cassidy, where does the root belong? In the denominator. So we're going to say negative 42 raised to the 2/7. And there's one extra thing that I need to add to this particular problem. Because I want to take the 7th root of all of negative 42, I need to include the negative in parentheses. So that when I would rewrite that, if I were going to do the 7th root, I would put the 7th root over all of negative 42, not just 42. Okay, so parentheses are important there. Okay. Let's rewrite in the other direction. Rewrite with radical notation. 19 to the 1/3, 6 to the 2/3, and negative 8 to the 3/4. They already look like rational exponents, so you have a fraction, and the denominator of your fraction is your root. So that helps you write it in radical form. 19 to the 1/3, the denominator is my root, so I'm taking the cube root of 19. Done. 6 to the 2/3, the denominator is my root, so I'm doing cube root of 6 squared. A 4th root, what do I put under the radical? 8 or negative 8? Is the exponent touching the 8 or touching all of negative 8? It looks to me like it's just touching the 8. What would I need to say touch all of it? I need parentheses. Do I have parentheses around that negative? No. So this exponent applies only to the 8. So I'm going to do the 4th root of 8 and cube it, and this negative just hangs out front. So you have to be really careful with the placement of your negative or the placement of parentheses. If you want it to be underneath the radical, then you have to have it in parentheses. Otherwise, it just hangs out in the front. Alright, so that's rewriting. You just have to use that rule from the last slide. Okay, the root always belongs in the denominator. If you have a fraction exponent, the denominator is the root. You're done. Okay. Now, we want to move on so that we can evaluate these roots. Not all of these are possible. We might need a calculator to get a decimal value here, but we're going to make a list of perfect numbers so that that can help you evaluate things if you don't have a calculator. Okay, so we're going to need about I'm going to do the numbers 1 through 10. So if you want to have a line for each number, then you need 10 lines of paper. Okay, so decide if you have enough space on the notes or if you want to squish things in to multiple lines. We're going to make some columns. I'm going to start with the very left column, which is just the roots. When I give you problems and you have to evaluate roots, they're going to have to be like fairly small numbers, because if I use a big number like 25, taking it times itself, it's already a really big number. Okay, so I'm going to pick some smaller numbers. In the root column, I'm going to do the numbers 1 through 10. And then the square column should be really easy for you to make, but it's a helpful column so that we can move on to the cube column. We're just going to square all those numbers that are in the root column. So 1 squared is 1, 2 squared is 4, and so on. I think you can probably fill that in with little troubles. And a lot of you can probably go a few more because you've taken geometry, so you're familiar with them. Okay. So taking square roots is pretty easy for us, but we're not as familiar with some of the other perfect numbers, like perfect cubes. So let's make a column for cubes. And this is a really easy way to get a list of perfect cubes. If you already know the perfect squares, then just take the perfect square and multiply it by the root. So like 1 times 1 is 1. And then we already know that 2 times 2 is 4. To make it a cube, we just need to multiply it by another 2. So 4 times 2 is 8. 9 times 3 is 27. 16 times 4 is 64. For 25, I think about quarters. If I had 5 quarters, I'd have $1.25. And I'll put up the next two. 36 times 6 is 216. 49 times 7 is 343. And that's probably like as high as I would go for a quiz, because 8 and 9 are going to be bigger numbers, and it's kind of hard for us to remember all of those. Although I do think that 10 cubed is fair play, because 100 times 10 is just 1,000. Okay, so the 10s are pretty easy to do. And some of you might be familiar with a few of those numbers as well. 1, 8, 27, 64. Those are perfect cubes. You might have used those before. Let's make a list for perfect fourths. Perfect fourths are easy if you've already made a list of perfect cubes. So now you're going to go to your list of perfect cubes and you're going to multiply it by the root one more time. So 1 times 1 is 1. 8 times 2 is 16. 27 times 3 is 81. And 64 times 4 is 256, but I really won't go much beyond that. I suppose I could write up 625. Then we can make a list of perfect fifths. So I go up my fourth column and I multiply it by another root. 1 times 1 is 1. 16 times 2 is 32. 81 times 3 is 243. Yeah, I'm done. Number's too big. And one more column. 1 to the 6th is 1. What's 2 to the 6th? 64. That's all I'd ever ask from that column. Okay. This is really handy, like if you don't have a calculator available to you, you can still evaluate roots using this chart. And I'll show you on the next slide, we'll do some evaluations. I'll show you how we can use the chart. I'll tell you how to do it in your calculator, and so you can decide how you're going to evaluate. Okay, my first example is 81 to the 1/4. To me, 81 to the 1/4 doesn't mean a whole lot. It doesn't mean 81 times 1/4, because if I wanted to multiply 1/4 by 1/4, I would just write it like that. I wouldn't write it like an exponent. Okay, so an exponent means something different. Okay. To give it more meaning, and you're asked to evaluate something, rewrite it as a radical. So remember, if you have a fraction exponent, the root is where in the fraction? Kyle, where's the root in the fraction? In the numerator? Yes, it is in one of the two places. Yes, the root is always in the denominator. You've been on your phone too long. I've said that like 20 times, haven't I? The root is always in the denominator. So we're doing the 4th root of 81. Now, if you don't have a calculator, I'm going to flip back to my chart screen. I'm going to show you how you can do the 4th root of 81. Okay. If you want to do the 4th root of 81, go to the 4th column. Is 81 in the 4th column? Yes, so find it in the 4th column, and then follow it all the way back to its root. The 4th root of 81 is 3. So you have an answer. It works out real slick. You're done. If you have a calculator and you want to see if your calculator can do roots, most of you have a button on your calculator for exponents. If you have the Texas Instruments, your button looks like sort of like an up arrow. It's called a caret. And if you have a Casio, a lot of times it's like x to the y or y to the x. Or it has like a little square for an exponent. But find your exponent button, and above your exponent button, it probably has, like on the plastic part of the calculator, it looks like a radical with like an X on the outside of it. So that's like your special root. Okay. And if you want to do the 4th root of 81, then you'd have to, in your calculator, type 4, then hit second or shift and your exponent button to get the special root. So then it looks like this in your calculator. You don't want the one that's the square root without the x, because then it will do 4 times the square root of 81, which is 4 times 9, or 36. Okay? But we want it to do the 4th root of 81, so we need that little x there. So see if you can make your calculators work with that. And I'm sure that the cell phone calculator, like if you're just doing your homework at home, or you're out and about doing something, I'm sure the cell phone calculator can do a root too. And Jace, you have the graphing calculator. Have you found yours? You know where yours is? Oh, does it have it on there? I don't know. Let me see. No. So like you would do. No, that's the square root. So like you do 4 and then hit the math button. And the ground over there. And you see the special one? 5. So you choose 5. Anybody else having trouble finding theirs? This is it. So do you do things backwards usually? Okay, let's try. 4 for the index. Second, y to the x, 81 equals, no. So you try 81, second, x to the y, 4 equals. So you have to put in your radicand, then shift your radical, your index. Okay. Good. Anybody else having troubles? Okay, let's do 2 more. 16 to negative 1/4. Ooh, this one's hard. Not hard, but easy to mess up. What's weird about this one? Has a negative exponent. Remember from our discussion yesterday, negative exponents do not make anything negative. What do negative exponents do? They flip what they touch. So does the 16 flip or does the 1/4 flip? You flip the base. Right? So like in this question from our homework that's up here on the board, the x flips to the top. So we're not going to flip the fraction exponent. That's what most people will tend to do. They'll want to flip the fraction exponent. You're actually trying to flip 16. So instead of being just regular 16, it's now 1/16. You've just flipped the base. So you flip what it touches, not the exponent. And then the exponent becomes a positive 1/4, which we could take a page from our previous problem. 16 to the 1/4 doesn't really mean a whole lot to me. So I'll write it as 1/4 root of 16. And what's the 4th root of 16? Use your chart or your calculator. Faith says 2. So 1/2. One more. 4 to the 3/2. Okay, remember, this does not mean 4 times 3/2. If I wanted you to do 4 times 3/2, I would just write it as 4 times 3/2. I wouldn't write it like an exponent. So you have to remember, exponents are something different. When you have a fraction exponent, the root is always in the denominator. So what root am I taking? The square root of 4, and then I'm cubing it. What's the square root of 4? 2. Cubed is 2 times 2 times 2. 8. Done. Be careful. Does anybody have any questions on those 2 examples? Okay, we have one more thing to talk about. I'm going to have you write this down in your notes. Solving equations in the form x to the n equals a. We're getting a lot of information today. You'll have an assignment so that over the weekend you can work 10 problems, kind of review the concepts from today. On Monday, we're having a second day of 5-1. So thankfully on Monday, I won't be standing up here talking the whole time and doing examples. You'll be doing examples. You'll be rewriting. You'll be evaluating. Okay, so you'll get a lot of practice as well on Monday. If you have an equation that looks like x to the nth equals a, to get rid of the exponent of n, just take the nth root of both sides. You did this all the time in geometry. When you did Pythagorean theorem, you would get down to like c squared equals 36, and then you would take the square root of both sides. And we did that in quadratic unit. Okay. The only difference in algebra is we can come up with more than one answer in some cases. If you're taking an odd root, you'll have only one answer, okay? So the odd roots, you can take of any kind of number. You can take odd roots of positive numbers, and you can take odd roots of negative numbers. Because a number can multiply by itself an odd number of times and end up being negative. Okay. You keep the sign of the radicand, the thing underneath the radical, if you're doing an odd root. So if I'm doing the cube root of 8, it's 2. If I'm doing the cube root of negative 8, it's negative 2. It keeps the sign that's under the radical. For an even root, I should always have 2 answers because I'm going to always add the plus or minus. So in geometry, you didn't include the plus or minus because you'd only get one answer that's positive distance. Last chapters in quadratics, we said we have to have plus or minus because we don't know if it was 6 times 6 or negative 6 times negative 6. So the same is true in this chapter if it's an even exponent. Okay, got to add the plus or minus. So here's an example of solving an equation of the form x to the nth equals a. And I'm going to then take the same example. I'm going to change it in a couple of different ways just to show you how you'll use reverse order of PEMDAS. X to the 5th equals 32. Well, you want to get x all by itself, but it's being raised to the 5th. So what am I going to do to both sides? Take not the square root, the 5th root, right? The square root will undo a 5th. We need a 5th root. So we're going to take the 5th root of both sides. And this is where evaluating roots comes in handy. What's the 5th root of 32? 2. So you have an answer. Because it's an odd root, I should keep the sign of the radicand. The radicand is positive, so 2 is the only number that works. Negative 2 will give me negative 32, so I don't include it. What if I change this problem? So I make it x to the 5th plus 10 equals 42. What do you do first? Subtract 10 first, right? And then you come up to the same problem and you get the same answer too. What if I change it like this? X plus 10 squared. No, to the 5th. I meant 5th. X plus 10 to the 5th equals 32. What do you do first? Can't undo the 10 because it's in a group of parentheses. Well, you want to undo the 5th, so what undoes the 5th? A 5th root, right? You're going to start by taking the 5th root. We did problems like that back in chapter 3, where we took the square root. So we take the 5th root of both sides, and then we'll just have x plus 10 equals 2, so x must equal negative 8, which is minus 10 then. So you just have to think about order of operations. When are you going to do certain things when solving? But at some point, to get rid of a 5th, you're going to have to take a 5th root. Okay? You might have to add, subtract, multiply, or divide something else along the way. Okay, your homework assignment then